Well, we have a new problem again, part of the homework for class 12 students. And the problem is three particles with same charges are initially are at three particles with the same charges at the initial moment are kept at the vertices of a triangle with sides r1, r2 and r3. The particles are simultaneously released, and they fly apart so that the segments connecting any pair of particles remain parallel to the original ones. Oh, similarity is getting maintained. What is the mass ratio of these particles? M1 is to M2 is to M3, and we have to ignore the gravitational attraction, of course. So this is a great problem, no doubt about it. And we have initially a triangle like this. So though it's not done, so here we have a triangle like this, three masses M1, M2 and M3. The side lengths are R1, R2 and R3 like this. And now after some time I can see that they will become something like this. So that M3 comes here, M1 here and M2 here, and suppose this length is R1, this length is R2 and this length is R3 now. So according to the conditions of the problem, at any moment of time the ratio of distances R1 is to R2 is to R3 remains equal to the ratio of initial distances R1 is to R2 is to R3. Since the particle configurations are similar triangles for the same region, if we take angle alpha here, angle alpha 1 here, alpha 2 here, alpha 2 and here alpha 3, the angles alpha 1, alpha 2, alpha 3 at the vertices remain unchanged. These angles remain unchanged. Like this angle is alpha 3 and this angle is alpha 3, this angle is alpha 1, this angle is alpha 1, this angle is alpha 2, then this angle is alpha 2. And if we can draw a perpendicular from here to here, this side, let's call it H. It's a perpendicular. If I can draw it, and these two sides, this side and this side, these two sides are parallel. That means these two sides are parallel only in the case if the projections of the velocities and acceleration of the particles m1 and m2 parallel to this perpendicular. That means this thing which is perpendicular to this, and these three sides are parallel, this and this side. And what I'm trying to tell you that if these, I'm using simple concepts, if these two sides are parallel, then the projection of velocities and accelerations of masses m1 and m2 along this perpendicular should be equal. That means if its acceleration is a2, and because I don't have any information about velocities, but velocity and accelerations, because they are moving parallel to each other, so they must be same. If the acceleration of m2 is a2 and its component perpendicular to this line is, that means parallel to this line, is a2 perpendicular, and this suppose the acceleration of m1 is a1, and the acceleration component perpendicular to this line and parallel to this line is a1 perpendicular. This a1 perpendicular should be equal to a2 perpendicular. And what is a1 perpendicular? So m1 is acted upon by two charged particles. One charged particle is here and another one is here. And since we are considering about a component perpendicular to this line, so these two forces will have the force acting between m1 and m2 will have no component in the direction of a1 perpendicular. Only this force will have a component in this direction, and this force can be written simply as I'm writing a1 perpendicular, and this can be written as k charges, or charges on all the particles are same, so kq square divided by r1 square, r2 square, the distance between them is r2, so r2 square. And since this force is acting in this direction, so its component will be here, or here sine alpha will be sine alpha 1 divided by, since I'm writing the acceleration, so I have divided by the mass of the particle. And a2 perpendicular in the similar manner can be written as kq square divided by r1 square, and sine component is sine alpha 2, and even the component, yes, sine alpha 2, and actually a1 and a2 they should not be in this direction. Actually perhaps I'm making this mistake from earlier. a1 and a2, I am not concerned about the components of a1, in the accelerations of a1 and a2. I'm bothering myself about the acceleration components perpendicular to these two lines, and this is a2 perpendicular and this is a1 perpendicular. Yes, and this angle is alpha 2 and this angle is alpha 1, and this is perpendicular. So the sign is all right here, because sine alpha, sine 90 plus theta, or sine 90 minus theta, They are both thetas, sine thetas, so no problem here. And so these two equations are correct here. And one more thing we can get from this triangle, that this h will be equal to r1 sine alpha 2, and this h is also equal to r2 sine alpha 2. That means I can write this thing here, h is equal to r2 sine alpha 1, r2 sine alpha 1, and r1 sine alpha 2. So and that means if I can use them, both of them together, or simply I can divide them. That means kq square sine alpha 1 by m1 r2 square divided by r2 sine alpha 1, and I can write in similar way kq square sine alpha 2 divided by this thing. I think here also I left writing, I forgot writing m2, and divided by m2 r1 square r1 sine alpha 2, and then after calculation what I am going to get here is 1 upon m1 r2 cube is equal to 1 upon m2 r1 cube, and that means m1 is to m2 equals r1 cube is to r2 cube. And in the similar manner we can get m2 is to m3 equals r2 cube is to r3 cube. Therefore we got our answer, m1 is to m2 is to m3 is equal to r1 cube is to r2 cube is to r3 cube. And that's our answer. Thank you very much for watching.